Okay, class, what I'm going to do here is provide you with an example boycott decomposition on a relation that will give us something that is lossless but not dependency preserving, right? So if I have a relation with the attributes A, B, C, D, and E here, right, and I have the functional dependencies of A functionally determines B, B functionally determines C, C functionally determines D, and D functionally determines E, what I'm going to do here is look and determine what my primary key should be, alright? So, kind of help us along this process. I know A is always on the left side if I look along here. I know that B, C, and D is on both sides of some of these functional dependencies. I know that E is only on the right side. So I know E is not going to be one of my keys. So I know it's either going to be A, right? It's going to be that, or it's going to be A, B, C, D, right? The ones that are in the middle, along with what's on the left, right? So I know A closure is just A, B, C, D closure, reflexivity is all those things, and then D functional determines E is that, right? Oh, actually on A closure, it's A, B, C, D, and E, right? I can follow the chain across in this case. So I have all that. So BCNF violation? No, because D functionally determines E, right? It's this one here that shows that we are not in boycott normal form. So I need to decompose this, right? And now, if I'm really fortunate, I can pick some pairings that will preserve all these dependencies, right? I can look at this and know, based on this other possible candidate key, that I could do this, right? And I could do this, right? There's your D, there's your D. And I get something that is also dependency preserving, right? I could get fortunate, but I may have, went through and did it and had this and that as well, right? I could have did that, and that's not dependency preserving. That is. Let's say I didn't have a real good clue of how to do the decomposition, though. Then what I could do is to follow this particular procedure that has main steps and decomposition steps. So I'll take some Z, set it to all the attributes in my relation, and I'm going to look for violations, right? And there's other things that could cause a violation here, not just the D function determines E. So let's look at this. Let's see here. What do I want to do? Let's look at R minus AB, right? So that gives me CD and E. I look at its closure, and that gets me CDE, so I'm okay there. And that's by reflexivity. So I started with AB, now I'll take A and C, right? So AC, that gives me BDE, and then I'll take the closure of that. That gives me BDE by reflexivity, and B functionally determines C from above. So I have a violation here because of this and this. The C here, and then the C back on the alpha beta, the R minus alpha beta side. Okay, so go to my decomposition step. There's my main step, there's my decomposition step. So now I say y is equal to A, B, C, D, and E. So again, I just bring this down here. Yeah, I just basically will end up with the same thing by doing this. And what I can do now is eliminate one of the variables out of here, right? And it's since it's only the one that causes the violation, I'll take out the C here, right? So now I have y equals A, B, D, and E, right? So now I'm going to look for violations of that. Right? Let's see here. And starting with pairs, y minus AB, that gives me DE closure, right? And I do that, and that gives me DE. Okay, can't do that, so A and D now. And that gives me BE closure. BE, I take closure of that. BE by reflexivity, and then B functional terms C, C functional terms D, D functional terms E, which is already there. So here's the D, here's the D, so now I can, just like I eliminated the C from Y, I'm going to eliminate the d from y. Right? So now y is equal to a, b, yes. Let's see here. Is that what I wanted to do? Yeah, I wanted to. Yeah, I think that's what I want to do. Okay. So now I have to take combinations of this. Oops. Just E closure, sorry, my bad. And E closure is just E. So now I'll take the next one. B closure, that gives me B by reflexivity, B functionally determines C, C functionally determines D, D functionally determines E, right? So there's the D, there's the E there. So that just leaves me with Y equals AB. And I have essentially my first decomposition, right? R1 equals AB. So now I have this, and what I can do now is go back to my main step and look for violations with, and also when I do this, I do R minus the alpha or the left side, so my R2 then, you know, from the original relation with A, B, C, D, and E is going to be on here, B, C, D, and E. So let's do that. I ran out of paper. Did I run out of paper? I think I ran out of paper. Well, let's see if I can get it done with the back side of this. Maybe that works. So I go back to my main step, right? And what I'm going to do now is I have my R1 equals A and B, and my R2 is going to be B, C, D, and E. And now I'm going to look for, based on the original functional dependencies, not on the original function. I need some F closures. I might need them. I'm not sure. But I know from the original functional dependencies, like by transitivity, A function determines C. I have B function determines E, right? And then C function determines E on that. So now I'll have those. Or B functionally determines D. Yeah, it's D, not C. Or E, yeah. So yeah. So there's some other things that would go into F closure. Let's see here. So C is equal to BC. This one's just two attributes, so that's already in boycott. We just did that part, so we know we don't need to look at that one any further. So we look at BCDE. So we'll take them in pairs. That gives us DE closure to look at. DE by reflexivity, and that's it. So no violation there. So take BD. So that will give us CE closure. And then that will give us here C, D, and E, which gives us a violation here. So now what we can do is go to our decomposition step. Bring this down here. Just kind of replicate that. And we can now eliminate D from Y. Right. Now Y is equal to B, C, E. This will give us R minus SCPC, try that. That gives us E. E closure is just E in this case. So let's try R minus BE. That gives us C closure. Let's look at that's C, D, and E, right? So there's a violation. So now we can eliminate E from Y. So now Y is equal to BC. It's just two attributes. By theorem, we know that this will give us some that's in Boyd conormal 4. So now R1 is our AB, our R2 is our BC, and our R3 is, again, this is going to be R minus the alpha, which is, whoops, DB, right? So from this one up here, right? So CDE, right? So we go back and actually that. Yeah, B, C, and C. Well, let's see if we go back to our main stuff, we'll see any more violations. Alright. So Z is equal to CDE. So now let's look at R minus CD. It gives us E closure, that's just E. We'll look at CE, that gives us D closure. It gives us D and E. Alright. So there we go, there's an E, there's an E, there's an E. So we go to our decomposition step. Reproduce that. Oops. Try that again. So we have our E, so we can eliminate E from Y. Two attributes, we know that's going to provide us with something in Boyd conormal form. So we go back up here. R1 is AB, R2 is BC, R3 is going to be, in this case, CD, and R4 is going to be, again, we'll take the left-hand side of this, which is the C, right? Subtract it from the CD, and that leaves us with our D and our E. Alright. Now, this actually is, based on the original functional attributes, I actually do believe that's dependency preserving in this case. Yes. So, in this case, it just happens to have kind of worked out. Right? So we have these four. I would have said earlier that that R1 and R2 before I had was kind of preserving was because your primary key up here was all these four attributes. You could determine everything all at once, each individual row, because all the attributes are the key. And then you had the separate one for D, function determines E as its own separate thing. Here, we went through the process of breaking this down into four subschemas. These each preserve an individual functional dependency from the original, right? A, B, B, C, C, D, and D, E. So this is actually, in this case, dependency preserving. We have something that preserves each one of these functional dependencies in this case, all right? So I hope that makes a little bit more sense and provides you with a mechanism for doing the decomposition. Thanks. Have a good day.